Hey everyone, this is Ayush Tandon and welcome back to my channel. And today I'm gonna have a discussion on the topic ozonolysis. Now, ozonolysis is one of the most crucial part which you study when you prepare for engineering in the chapter from hydrocarbons, and then in various rearrangement reactions. Ozonolysis is a major part, and we are gonna discuss today the basic part which you can study, and this will give you an overview of what is ozonolysis. So let's begin without wasting any time. Suppose this is an alkene. As you can see, all the substituents are different, and I have specially taken a H. Otherwise, there is no particular reason, but just to make you sure that an H can also be there. Now the reaction goes something like this. I have made a PDF and I've written the whole mechanism, and we are going to discuss today the mechanism. So O3, what happens? Now let us understand that ozone has a structure like this. So the oxygen atom which has a positive charge is sp2 hybridized. Oh sorry, S- sp2 hybridized, yes. Uh, so it is most likely to have a 120-degree angle between the oxygen double O double bond and O single bond. So the bond angle will be 120 degrees. Now the reaction proceeds like this. Step 1. Step 1, this is the alkene which you see, and what happens is that this double bond, the electron, these pi electrons transfer to this oxygen atom. The pi electrons of this double bond transfer to the oxygen atom which has a positive charge, and this oxygen atom which has a negative charge transfers its electron to this carbon atom, the different carbon atom. If this is R1H, carbon is C1 and this is C2. So you can see it is called concerted mechanism, and by this the image which you will get is something like this. This is the image you're gonna get. From this atom, this was a double bond, and this is the electrons are transferred, and this structure is called ozonide. Yes. Okay. Now, by the this is not a very stable species, and step two is that by rearrangement, uh, it transfers to become this, and this is called ozonide. So let me just tell you the difference between ozonide and ozonide. So here, as you can see, all the oxygen atoms are joined together, and whereas in this, one oxygen atom from here actually joined on the opposite side. So what is the mechanism for this rearrangement? So I'm going to present you a very small mechanism, and this will be the basic step for this conversion. Let us discuss the mechanism for this rearrangement. Now as you can see, these arrows, what do they basically indicate? The first part of the step 2 is that this single bond breaks and is transferred to the oxygen atom of the carbon 1 atom, and then the topmost oxygen atom uh, gains the electron from the left oxygen atom. And now the third part is that the other oxygen atom shares its electrons, the valence electrons, and forms a bond C2 here. Okay, and a C2 bond, carbon oxygen bond. So you can have a look at this and you will understand that this is also by concerted mechanism. So after this type of mechanism, what happens, you get R1C double bond OH, so you get an aldehyde, and then plus you get some ketonic species, okay, uh, which you can call And as you can clearly see, this oxygen, the oxygen directly attached to the C2 atom will acquire a positive charge, and the other oxygen atom will definitely acquire negative charge, because uh, this oxygen, the electrons were transferred to this, so it will definitely gain a negative charge. Now you get these two species. Now again, we wish to obtain some more species in which there are no partial charges, or any charges developed. So the step other step is this. I have drawn it clearly over here. Yeah. So here, as you can clearly see, this is the first species, R1C double bond OH, and here it is R2C R3, and this double bond O, and then single bond, and then O minus. So the electrons are transferred to this C1 atom, the oxygen atom acquiring a negative charge, uh, transfers its electron and shares its electron with carbon 1. The oxygen atom on the carbon 1 carbon oxygen bond. So the pi bond, the electrons of the pi bond are shared with the carbon 2, and the carbon 2 and oxygen bond, double bond, so the pi electrons are transferred back to the empty p orbital of the oxygen atom. So by this mechanism, the final products that we get we get ozonide. Yes, this is the ozonide. So as I clearly showed you this, so this is the inverted image. Um, well, I've just drawn for convenience here, just like this. So you can see there is a pentagon formed, and of 3 oxygen and 2 carbon atoms. And the last step is the addition of hydrogen, water, and you get R1CHO and R2C double bond O R3, and you get a nascent oxygen. Now this nascent oxygen will oxidize the aldehyde and will give you the carboxylic acid of R1, and the products you can say R2C, you get a ketone and a carboxylic acid, and this is called oxidative ozonolysis. Let us have a look at the reductive ozonolysis. So if you just obtain the ozonide species, there we added just water, and if you add zinc dust along with water, you will get R1CHO plus R2C double bond OR3. So there is no oxidation of the uh, aldehyde form. So this is called reductive ozonolysis. Yeah. The last thing which I have here is that this ozonolysis can also be applicable to the an alkyne. So ozonolysis can also occur with alkynes. So when they perform ozonolysis, just like ozonide, we also get um a similar ozonide here as well. But see, there were 3 bonds between carbon 1 and carbon 2, let me call. So it is interesting to know that uh, 2 bonds are broken and here 1 bond is left. So there is a bond connection between the carbon atoms. Whereas if I show you there the ozonide here in alkene. So in alkene, here you can clearly see there is no bond between carbon 1 and carbon 2, but here there is a bond because of that triple bond. And when you again add Zn dust plus H2O, you're gonna get this. Now, oxygen gonna form a double bond on both carbon atoms, and we call this is called vicinal diketone. Yeah, this is called vicinal diketone. A special fact to know, that I've taken this example as well. So as you can clearly see, there are two. This is a compound, and there are two double bonds present here, and the reaction says that if we add O3 next, it's very important to mention that, because sometimes if you do not write X's, so uh, the candidate thinks only one bond will be broken, and just for safety, so it basically means that all the double bonds, so there's no deficiency of ozone here. And the first step is to add addition of ozone, and the second step is addition of Zn dust along with water. So the basic key principle here you should consider is that we saw this example. So basically, when we first add ozone and then Zn plus H2 or reductive ozonolysis again, so wherever the double bond is present on that carbon atoms, you just put a double bond oxygen. So see, I've shown you like this. So I just separated the both carbons, and I formed a double bond, carbon oxygen double bond. That's it. So if you wanna remember it as a trick, for these examples it should work, but in complex situations you have to uh, recall the mechanism and then analyze, and then you have to see what will be the end product. Is the oxidation favorable or not? Here if you see, you just break this bond as I have shown by this wavy lines, and just attach oxygen atoms on both the carbon atoms, which are bonded by double bond here, and this there will be this bond breaking, and you will definitely get how many products. Now in these examples, the real question is, how many products will you obtain? Well, if you clearly see, this will be the product 1, then this will be product 2, and this is gonna be the product 3, and along with the addition of oxygen atoms. So what do you get? You get propanol, you get propane 1,3 diol, and you get pentanol. That are the three uh, products of this reaction, and obviously this is the reductive ozonolysis. Hope you like this video. This video covers all about ozonolysis, and thank you for watching.